All right, here we go. Move back, please. Move back. Good job. You guys are good at that. You get right to business. That's good. Zach, just let him do his own thing.
Charlie's got a bad leg.
Charlie's okay.
He does have bad leg.
What happened, Charlie?
He broke it a year ago.
Oh, it's still doing it. You looked okay when you were running around. All right. Who knows the answer to number one? Who wants to share with the class? Go ahead, Ryan.
Well, essentially, excuse me. What happens is when it gets to the boiling, it starts evaporating, and then the stuff that evaporates brings the heat out with it, so it stays at constant.
Exactly. Very good. Very good. When water or liquids boil, they hit that boiling point, and then the extra heat goes into breaking those forces and takes the heat with it when it evaporates. So the liquid never can ever go above its boiling point. Can boiling point change?
Yes.
Yes. How do we change it?
Pressure drops.
Air pressure, right. I'm going to show you that today. So if you change the air pressure, that temperature can change, but if something is actually boiling, wherever it is, whatever room it's in, whatever environment, that temperature will never go above that boiling point because the extra heat goes with the vapor and it goes into breaking those forces of attraction. So that's good. That's important to understand. And number two, what's the equilibrium mean again? Raise your hands. Someone besides Ryan. Xavier.
When the forces.
Is that B? I don't mess with B's, man.
All right. Hey, it's all right. It's a line.
I'm allergic, man.
We should put them in the vacuum chamber.
Oh my god.
Oh, I don't mess with
It's not a
B.
B.
Put them there.
I don't think that's a B.
Mr. McCoy, if you can catch that.
It's
I
got
don't
like
really
a
want to
12.
catch it.
Mr. McCoy, can I kill it? Mr.
Oh,
McCoy.
that's the girliest thing I've seen all day. Oh, it's
Oh my god, it's out! No, I gotta get it off!
Where is it?
It's over here! Hold on,
It's a stink bug.
Yes, get it off!
Better not
Hey,
be.
come over here. Come over here.
Oh, really on me? On everybody else and put on me?
I'm allergic to bees, that's why.
What?
I like Mr. McCoy's reaction.
How did it smell?
I thought it was a bee coming out my face. It's a stink bug.
Oh.
And that's on film, too.
That was really girly. That was really girly.
Anyways, back to this. It happens. Equilibrium. It's not when forces are equal. Give me explain it. How about just answer the question?
Well, when the liquids contain.
Hey. Go ahead.
When liquids contain, it's evaporating and condensing at the same time.
Very good. That's equilibrium, where we have a contained liquid, evaporation and condensation at the same time, but give me another word. Rate. Same rate. So the rate of evaporation equals the rate of condensation. So that's it. That's the explanation to the question. What's building up in here? What kind of pressure? Vapor pressure, because vapor particles are doing what? Colliding, bouncing around. It's called equilibrium vapor pressure because it can't change. This bottle's not going to just spontaneously keep building pressure and blow up. It can't. This is why. Because you have a set number of particles up here. Because anytime more vapor tries to get out, what happens?
More goes in.
More condenses. So it stays constant, so it doesn't increase or decrease in pressure once it reaches equilibrium. It takes a little while. First, evaporation is going to win. It's going to win for a while, then condensation will catch up, and then you'll have an equilibrium. So that's what the video was talking about yesterday. So I think I probably linked it on my website. If you miss class, I pretty much have everything either on YouTube or on my website. But anyways, there's those two questions. I got one more Regents question. I'm going to pop up here quick, then we'll go back and do the demos. And if anybody has big marshmallows at home or normal size, the little ones don't work as well. So I'm going to put these in the vacuum chamber, but the normal size ones work better.
What's another thing I can put in the vacuum chamber? Tell me more thing. Elbow cooler.
I don't know, give me a minute, because it's got to be safe. Oh, sorry, we're still on that.
Hot loaf of bread.
That's not going to do anything.
I agree.
Wait, what
The soda can.
there's stuff that's dangerous?
Yeah,
All right, we want something soft.
Yeah,
Like a
so
soda
like,
can.
Oh, I didn't hook it up.
Like metal or
Soda
What about
can. See the soda can go.
Like what?
Or metal?
Metal? No.
something
What
soft.
about grape?
Yeah, I was thinking grape, but I don't think it's going to do anything.
So it has to be soft like that?
Okay.
Gum.
It's porous.
Irritating now.
What about
Chewed gum though.
what
Yeah.
about
Ew.
banana? A part of a banana.
You just
It's
go
not
rush
gonna do
to
it.
it. One out of 5 people.
Okay, right here. All right, stop talking. 41. At 50 degrees, standard pressure, intermolecular forces of attraction are strongest in a sample of. Don't answer out loud. I see some people getting their reference tables out. Why would that be?
They're brave.
Table H, right? Everyone go to table H, please.
Oh yeah.
This is a good Regents question for table H. Oh, and we got to go over the bookwork too. I skipped that in my.
We'll do that after.
No, we got to get the homework done first, then we'll do
We'll do
that.
that
We will have time for the demo, I guarantee. If anything, we'll have less time for notes. That's it.
Yay.
We'll do the demos. Okay, go to table H, and I'm going to tell Jenny that you do not need that number to answer this question. Why?
You want me to answer?
Well, I just want you to tell me why we don't need that number to answer this question.
Because it doesn't matter. It's like
Very good. It doesn't matter what temperature they give us. Why? What's the answer?
because it's always ethanolic acid.
Good job. It's always number one. But how do we know that though?
It has the highest boiling point.
Very good. It has the highest boiling point, 117, 116. That means it has the strongest intermolecular forces. Very good. Why do they give us the 50? They give us the 50 because they want you to go to 50 and then go up to the lines, but ethanoic acid is the lowest. What does that mean? What does that mean? It's the lowest. It's always the lowest. What does that
The
mean?
strongest forces of attraction.
Yeah, but yes, good. Strongest force of attraction. What else does this chart tell us?
But the other ones have weaker forces of attraction.
Yes, that's good. We need to know that, and that's good. But let's talk about this now.
The pressure?
The vapor pressure of ethanoic acid is always
Low.
lower than all the other liquids. What does that mean? Devin, what does that mean? If something has a low vapor pressure, what does that mean?
It doesn't give off as much.
Doesn't give off a lot of vapor. Very good. So if ethanoic acid doesn't release a lot of vapor, that means the vapor can't do this. Collide. If it can't collide, it has low vapor pressure, which means, Ryan, what did you just say over and over?
Oh, the higher, stronger forces.
Stronger force, right. If it has strong forces, the particles are stuck together, so they can't evaporate as easily. So I'm basically done with this. We've done, I feel like, a lot of it. I think you guys, a lot with it. I feel like you get it. Just don't forget, this is standard pressure. This one is the strongest, that's the weakest. Look at the boiling points, but also be able to explain how low vapor pressure and high vapor pressure also affect the forces, right? Or how you can look at that to figure out the forces. Low vapor, strong forces, high vapor would be weak forces. All right, good. Let's go over the homework, and then we'll go back. All right, so 435, number 70, I erased it. 435, 76? Yeah? Okay. Here we are. And I want everyone on the page because there's something else I'm going to talk about on there that you need to see.
What page is it?
435. 76. Compare boiling and evaporation. I'm just going to answer this to save some time. Boiling is when the entire liquid evaporates. Evaporation is when just the surface evaporates. Why? Why, when it boils, can all of the liquid evaporate? What's the definition of boiling? Anyone remember? That's kind of part of the next question, 78. What is boiling? Temperature at which?
It starts to evaporate.
No,
Temperature at
when
which
the
the
vapor
whole
pressure
thing
equals
is
the air pressure.
Vapor pressure equals the air pressure. That's when liquids boil. So vapor pressure pushing up, air pressure pushing down. When those two equal each other, it boils. So that's why the whole liquid can start evaporating when it boils. Evaporation, just the surface, has enough energy to break free. 78, relationship between vapor pressure, atmospheric pressure, and boiling. All right, if we increase air pressure, what happens to the boiling point? If we increase air pressure.
Oh, it goes up.
Right, boiling point goes up because you're pushing down, right? Think of the air pressure as a force pushing down the liquid. So if you increase that force, you need more energy to push back. So boiling point goes up. If you decrease air pressure, that means your boiling point goes down. So there's a relationship between those two. What about vapor pressure? We could say low vapor pressure means high boiling point, right? Because that's strong forces. High vapor pressure, low boiling point, because that's weak forces. That's another relationship. And then the last thing is what we just kind of said. Boiling point is when vapor pressure equals air pressure. That's the definition of boiling. That was it for that page. Go to number 81. Look above 81. You see that little diagram? Looks familiar. What is it? Above question 81. What is that called? Phase diagram. Says it right on. What would the green area be? Solid. Good. What about the yellow? Liquid. And then the blue? Gas. Jake, what do you call that point where all three of those colors meet? Triple point. Very good. Triple point. Moving on. 436. Number 86. All right, someone tell me why density of mercury is greater than density of water at the same temperature and pressure. Who's it going to be? It's going to be... Where do you think? Why would mercury have a higher density than water at the same temp and pressure? What am I trying to say? Perfect. Yes, perfect answer. They have stronger intermolecular forces. They meaning the mercury. Mercury has stronger forces. What's density really all about? Taylor, what's density all about? Something is very dense or not dense. Like this table is very dense, but the air is not. What really dictates density? Yeah, how close the particles, how compact it is. Very good. So mercury's particles are closer together. It's more dense, stronger forces. They're attracted to each other very closely. Good. And and kinetic molecular theory, you're supposed to talk about that. All that means is how it's arranged, like we just said. Particles are close together. So not only does it have strong forces, but we should have also said that brings the particles closer together. 87. All right. We had trouble this morning with this question. So if you have two identical containers, okay, let's say they're about the same size. Let's say they're 1 liter each, and they're both at 25 degrees Celsius. This one, 2 ATM. This one, 1 ATM. I had an analogy, but I don't think it was very good, so I'll try and do it a little different for you guys. This sample has a certain number of gas particles in it. This sample has a certain number of gas particles. Avogadro's theory or hypothesis is if you have the same volume, same temp, same pressure, you have the same what? Number of particles. So if this was 1 ATM and this was 1 ATM and the volumes were the same and the temperature is the same, then I would have the same number of particles in both. But the pressure here is double. What does that mean? What does that mean, Nicole?
More particles.
Yeah, how many more?
Double.
Probably twice as many. There's twice as many particles in here. There's twice as many particles in here. Think about it this way. Think about marshmallows. Maybe this analogy will help you. If I have an unlimited amount of marshmallows, okay, I put, let's say, 500 marshmallows in this box, but I put 1,000 in this box. So twice as many marshmallows. Wouldn't this be more crowded? Yes, and it would be harder to fit, tighter packed. Same concept for gases. If you put twice as many particles in here, they're going to be more packed, closer together. Well, if gases get really close together, what do? Gas particles are put really close together. What do? What's that? They build up pressure, but why? What causes pressure? Collisions. So if you put more particles in here, less space, there's more collisions. That's why the answer is there's more particles inside this. I don't know if they want exact number, but there's more particles in the container with twice the pressure. Hopefully that makes some sense to you guys. And what do we here? 90? That was it? No. 89. Okay, you got sugar water. Let it sit out. Zach, water evaporates. Sugar's left behind. Is that freezing?
For 89?
Mm-hmm.
I said no.
Okay, explain why.
I said it was evaporation.
Very good. Water's evaporating. It's definitely not freezing. Shelby, why? Besides what he said. Yeah, water evaporates. Good.
Just, water wasn't,
89. In order for something to freeze, it first has to be what?
well, the temperature is not lowered. So, like, the water can't freeze.
We're not talking about water. We're talking about the sugar. I know you know. You know. It's just kind of a hard way to explain it. In order for sugar to freeze, it has to be this first. Liquid, right. In this example, you never have any liquid sugar. If you put sugar in water and it dissolves, are you melting the sugar? No, what are you doing to it? Dissolving it. So you still have little tiny solid crystals. They're just in the water. You can't see them. So it's just an example of understanding the difference between dissolving and freezing and melting. That's all. All right, 90, A, B, and C. I gave you the new pressures because they give you the question in ATM, but the graph is in torr. 760 torr is the same as 1 ATM. And then for number C, letter C, 0.8 ATM is the same as 700 torr. That's why I gave you those numbers. That makes sense, Bree? When you got to it? Okay. So A, the answer is 100 degrees. B, the answer is 78 degrees. And C, I would say about 98 degrees.
We didn't have to do C, right?
What's that?
I don't think we had to do C, right? Oh, we did.
Yeah,
I was
you're
just
supposed to.
checking.
Because I gave you A, B, and C.
I thought it was just A, B. Maybe not.
That's okay. It's not the end of the world.
Okay.
Questions on A, B, or C? Okay, put the books back, then meet me back there. Get your glasses on. Get your glasses on.